Okay, we now continue with a couple more theorems. So the first theorem is an obvious property that if you have two convergent sequences, Sn goes to S and Tn goes to T, then if you take a limit of Sn plus Tn, a limit of a sum should be equal to sum of limits. Again, first let's try to get the idea of how we're going to try to prove it, and then we'll actually implement the proof. All right, so in this case, if I want to prove that the limit of Sn plus Tn is S plus T, actually, let me modify the statement of a theorem a little bit, because limit of Sn is S, and the limit of Tn is T. So limit of Sn plus Tn must be S plus T. Okay, so then I want this quantity to be small when n is sufficiently large. I can open the parentheses, and I can rearrange terms so that Sn, I subtract S from Sn and T from Tn, and group. So if I group terms like this, then absolute value of a sum by the triangle inequality is less or equal than the sum of absolute values of Sn and S and Tn and T, and I want the overall sum to be, sum of these absolute values to be less than epsilon, and I can achieve that, for example, by requiring Sn minus S to be less than epsilon over 2, Tn minus T to be less than epsilon over 2. There is nothing magical really about epsilon over 2. I could have taken epsilon over 8 here and 9 epsilon over 8 there. The trick is that sum of these two numbers must be equal to epsilon. All right, so, and I should be able to achieve both of these because the limits of Sn and Tn are S and T respectively. So let's choose any epsilon greater than 0. And because the limit of Sn is equal to S, right, then by definition of a limit, we know that there exists capital N1, such that if n exceeds N1, then I can make Sn minus S less than whatever I want. In this case, I choose to make it less than epsilon over 2. Likewise, because Tn converges to T, there exists another number, capital N2, such that if n is bigger than N2, then Tn is closer to T than epsilon over 2, right? So 1 and 2 are just consequences of a definition of a limit for Sn and for Tn. Okay, so now if I make capital N a maximum of N1 and N2, if n little n is bigger than this capital N, then it must be bigger than both N1 and N2. Because n is bigger than N1, Sn minus, no, that's not true. Sn minus S is less than epsilon over 2. And because n is bigger than N2, Tn minus T is less than epsilon over 2. And so then, if I make n bigger than capital N, I can just follow the same inequalities as I used here in my idea. If I take Sn plus Tn minus S plus T, I can open the parentheses, regroup, use triangle inequality, and then from here, Sn minus S is less than epsilon over 2, and Tn minus T is less than epsilon over 2. So this whole thing is less than epsilon, and then we're done. We should be able to prove the same statement for the product of two sequences. So that would be a result established in the next theorem. If a limit of Sn is S and the limit of Tn is T, then I expect that the limit of the product is equal to the product of limits St. Again, the first step will be that we need to figure out what is the idea of the proof, and then we actually implement it in the proof. So in this case, because I want to show that SNTN goes to ST, I need to evaluate the difference between the product SNTN and the product ST. At the end of the day, I know that Sn goes to S, so I can make Sn minus S small. Tn goes to T, I can make Tn minus T small. So somehow out of this difference of products, I have to extract the difference between Sn and S and difference between Tn and T. And the way to do it, the standard way to do it, which we will use a few times in a sequel, is to subtract and add something. Where once you subtract something, then you should be able to factor out the term. So in this case, I will choose to subtract SNT, and then to keep things the same, I have to add SNT, so that actually nothing changed. And then I can see that for the first two terms, there is a common factor of Sn. I'll combine them in this way. And for the last two terms, there is a common factor of T, so I will factor out T and combine them like this. And then what you have is a sum of two numbers, absolute value. So by triangle inequality, this is less or equal than the sum of absolute values. And then absolute value of the product is product of absolute values. So both of these I can then write in the following way. And so now we have to make these terms small. So again, I can try to use my epsilon over 2 idea. But before getting there, I recall that Sn is a convergent sequence. And because it is a convergent sequence, then that means that its absolute value must be bounded by some number. So before we were saying that the set is bounded if every element of a set is, let's say, S is less than capital M, bigger than M. But I always can choose, let's say, I can choose the largest of two numbers, minus M and capital M, and in that way I should be able to conclude, so for example, if capital M is bigger than minus M, capital M is bigger than, minus M, then M should be greater than minus M. In which case S lies in the interval between minus capital M and capital M, or you can rewrite that as absolute value of S is less than M. On the other hand, if minus M is bigger, then you can change this. So if minus M is bigger than capital M, then this is less than minus M, so that means actually that M is a negative number, and therefore again S is inside the symmetric interval from minus M to M. So however you look at it, if your set is bounded from above and below, then you can always produce a symmetric bound so that your set lies inside the interval from minus capital M to capital M. And so I'm utilizing that property here because I know from a first theorem that we proved that the convergent sequence is bounded, so therefore it means that absolute values of elements of a sequence must be less than some capital M. So that means I can replace this guy by capital M and require that this term is less than epsilon over 2 and that term is less than epsilon over 2. And then you see that this will be achieved if these two inequalities are going to be true. Why am I using the fact that Sn is bounded by some capital M? Because if I used Sn, then I would write absolute value of Sn over here, and that's not so nice because if I'm dividing by Sn is just an element of a sequence which could be any number. For example, it can be 0, and I certainly don't want to divide by 0. And yes, and there are other issues with it actually, but I'm not going to touch those. So what we're doing, we're simply replacing Sn with the bound capital M, because we don't want to deal with quantities that are changing within. Okay, so if I can establish both of these properties, then I'm done. And I should be able to do it, right? Because I know that Tn minus T is getting small as n goes to infinity, and so does Sn minus S. So first, I'm just going to make precise the statement that I made about the bound here. The first theorem that we proved today said that if the sequence Sn converges, then it must be bounded. And so, because Sn has a limit, it must have, there must exist a number m greater than 0 such that absolute value of Sn is less than m for all n. And what I'm going to do, I'm going to take that number capital M, and I'm going to make m bar to be the maximum of capital M and the absolute value of a limit of a sequence Tn. So basically what I want to have the same number here and here. And also I want to avoid the possibility that T is going to be 0. All right, so we have that. So and then we again use definition of a limit twice. I pick an epsilon. Then because limit of Sn is equal to S, I should be able to find capital N1 such that if n is bigger than capital N1, then this inequality is satisfied. And likewise, in exactly the same way, for Tn, because the limit of Tn is equal to T, I can find the number N2 such that the same inequality, in fact, is satisfied by Tn and T. So now, if I pick n to be bigger than the maximum of n1 and n2, then n is bigger than n1, it's bigger than n2, so both this and that inequalities are satisfied. And now I'm going to follow the chain of arguments that I used when I outlined the idea of the proof. I take Sn minus Tn, subtract Sn Tn, subtract St. I add and subtract Sn Tn. I regroup. I use the triangle inequality. I use the fact that the product of that the absolute value of the product of two numbers is a product of absolute values. Then I use the fact that Sn is bounded, so all Sn's are less than m. I already proved that. And the absolute value of T is just a constant. And then m and T are going to be less or equal than m bar, because m bar was a maximum of m and T. So this inequality should be true. And then because n is bigger than capital N, both this guy and that guy are less than epsilon over 2m bar. So I'm adding two of these terms here, m bar cancels out, and you get epsilon. And so once again, we proved, by using a definition of a limit, we proved the property that the limit of the product, in this case of two sequences, is equal to product of limits. So next time we're going to look at the ratio of limits, or limit of the ratio.